Alright, so in this one I'm just going to continue the topic 3 practice questions on electric potential. I've done the first 2 pages, let's move on. The diagram below shows a uniform horizontal electric field, and then you have A, B and C. You're comparing the values of what? The values of the electric potential. So let's find out. So we already know from the previous video, it goes from plus to the minus, So that means this is my V and this is my V. If you're comparing the points, A has a higher potential than B and C. So it is lower at A is wrong. Lower at A than C, that's wrong. It is the same at wrong. It is the same at B and C, correct. So that means these two have the same. Yes, of course, because they're both next to the minus. So that means 4 only. All right. 2 protons are located here. Rank the net electric potential V at each point P. Here, here, and here. If you remember the formula, V equals KQ over R. So V equals KQ over R. And if there's more than one V, you will add them. V1 plus V2. Being a scalar doesn't really matter about the direction, you're just adding the overall. So now we will have to compare the distance here. So we have the first distance here and the second distance here, maybe double the size. Let's see. Over here, you can actually quickly see that this is the same as this, and this is the same distance as this. So the big D and the small d have the same values. So when I do KQ over capital D plus KQ over small d, so far the values would be the same. Let's double check with the final one. Over here and here, that is the same as the small d's, and this one is exactly the same as the capital D's. In this case, if you solve it for each one with numbers, it will end up giving you the same potentials. So over here, you're asked to find the expression associated for the electric field. So it's just a simple derivative, but the question is, when do you know you're supposed to do the derivative, and when do you know you're supposed to do the antiderivative or integration? So I'll quickly show you that before we solve it. The idea is it's asking for the electric field. We know the general rule, E equals V divided by D. But what if it gave you the field and it asked you for the V? V equals ED, VED. So the way I like to remember it is which one looks like a derivative, which formula is kind of set up like a derivative. You'll find that this one does, because dV by dx, for example, this looks like a derivative. So if I'm ever asked to find E, I know I will have to do the derivative. Over here, this looks like the integral. This looks like it because it's set up and they multiply with each other. So we would do the antiderivative, which is the exact opposite of this one. So for this one, what do? We multiply by the power, then we remove a power. Over here, you do the opposite. You would add the power, then divide by the power. So literally the exact opposite in the opposite order. All right, we're not interested in that right now. We're only interested in this. So to find the derivative, we're trying to find it in terms of x, y, and z. So we're doing it for each one. So let's look at everything in terms of x. I will do multiply by the power and remove the power. So that becomes 2 times 5, which is 10x. And you remove the power, so that just becomes 10x. 10x, that's all I'll get. If I do it in terms of y, well, there is nothing here. That will become 0, and there's nothing here. So y was just nothing. Okay. Z, let's check. Nothing here, nothing here. Remove the power, that just becomes 0 as well. So in terms of this, we're supposed to have a 10x. So this is wrong. Maybe. This is wrong. Maybe. So looking at this 10x hat, that we're having it in terms of all 3 directions. So I should have it like this. It should be 10x plus, well, nothing for the y, plus nothing for the z. So I will have it like that to tell me that I have the x value, I had the y and the z, and this is the result of it. All right. Which of the following statements are not true, talking about equipotential lines and surfaces? Equipotential lines are parallel to the electric field. What does that mean? So that means if I had a field, which is here actually going to the right, let me just use this field. Equipotential lines are the lines like that, crossing it. So for example, this could have been plus 10. This could be maybe plus 7, plus 6. I can't see anything. Plus 5, plus 4, and so on. It's decreasing. Each line is decreasing as you get towards the end, which might ended up at, I don't know, -3, for example. I don't know. So the idea is each line over here has a different value for V. So when this says they are parallel to the electric fields, equipotential lines being parallel, which means they're in the same direction, that means, well, that's wrong because this is not parallel. This is perpendicular, if you've noticed. So this actually already is wrong. For a point charge would be correct. If you had a point charge, the equipotential lines go like this. Why does it go like this? Because the radius is increasing. My distance is increasing, and along the radius, the distance is the same. So this is fine. Exists for any charge distribution. Yes, I could have a plus and I could have a minus, and then the uniform fields will change. We did a little simulation on this in class. You can actually get the simulation from the PowerPoint, and you can check. When it moves on it along the equipotential line, of course, no work is done because the distance is the same. Work is force times the distance. There is no distance changing because it's basically the same radius. So that's fine. And even if you look at the other way to find the work is QV, if I have the V here and the V here is exactly the same because it's equipotential. So that means there is no change in V either. That also tells me it will be 0. So there are two ways to tell that this one is correct. A is the wrong answer. Okay, let's go back to red. And this one, equipotential lines, which is the direction of the field at P. Remember, from here, plus to minus. This is a big number, that's a small number, so this will be the positive, this will be the negative. I know it's not -5, but it is a smaller number than 30. So this is a bigger positive, and as you keep going, it's going to get to the minus eventually. It will get to the 0 or whatever. So the idea is it's going to be going like that, from plus to minus. So the direction of the electric field, of course, will just be up. There we go. Electron goes from different, equipotential lines. So let's have a look at these ones. So check this out. I only care about the final and the initial. That's all I care about. So we have the values here. So for example, let's start with 1. So 1 goes from final to initial. That becomes 80 minus 50. 80 minus 50 is 30. Okay, let's look at number 2. That goes from 70 to 80. So final minus initial, 80 minus 70. So number 2 will be 80 minus 70. That's a 7, okay, equals 10. That's a difference of 10 volts. Number 3, so starting here and finishing here. So I goes from the final 80 minus 60. I'm just going to write 80 minus 60. And this is for the third one. 80 minus 60, that's the first one. 80 minus 60 is also 20, not also, there is no 20 here. Okay, fine. This one and this one, final and initial. Let's check. 70 minus 80, 4 is 70 minus 80, which is 10. So these two have, well, it's not really 10, it's minus 10 to be fair. But comparing just the magnitudes of them, you will realize that 4 and 2 are the same, and they are both less than 3, which is less than 1. So 1 is the greatest, and 4 and 2 are the weakest. I want from least to greatest. So we're looking for 4 and 2 being less than 3, which is true, less than 1, which is true. I can see this is the answer. Okay. Let's move on to the next one. We have these lines. I think I must have solved it already in class. Let me just erase that. Get rid of that. So over here, how does amount of work compare for all the cases? So W equals QV. W equals QV. So that's the change in V. So from P to Q, this is a difference of 15. From P to Q, that is a difference of 15. P to Q, a difference of 15. Same work will be done. W equals QV. So we'll get the same work done. Over here now, we're comparing the magnitude of the electric field, not the work. Let's talk about the field now. The field lines, as you know from the previous topic, if they're closer together, that means the field must be stronger. So in this case, I can see that this has the strongest field around P. This has a slightly weaker field, and this has the weakest because of the distance. So it'll be 2, then 1, and then 3. So I can say 2 is greater than 1, greater than 3, or I can do the opposite way. I can write 3 is less than 1, which is less than 2. This is less than, that's greater than. You can write it either way. That means, of course, D would be our answer. Very nice. Over here, we're now comparing the magnitude. So we're not comparing which set of vectors represent the magnitudes and directions of the field's forces exerted on this. So we're trying to figure out the forces. So basically the idea is deciding which one has a stronger field around it. This one or this one. The formula would be FEQ, F equals EQ. This is the idea. So comparing P and Q, I can see that the field lines are closer together at P, so that means this will be a stronger field than Q. So I should have a bigger arrow for P and a smaller arrow for Q, and the direction, well, from plus to minus, it must be going up. So that means B is our best answer here. The amount of work done to move a positive charge in an equipotential surface, what basically means it's moving around the equipotential surface. So it doesn't really matter. Both work done are actually going to be 0. If I had an equipotential surface of 1,000, 1, 2, 3, and I had an equipotential surface of 10, there, moving around this is the same as moving around this. I know this is a bigger V, but the change of V will be the same. Actually, it will be no change of V. The only time you'll get work done is if you go between the V's. So that means, in this case, they're both 0. So we can consider that as the same. Both are going to be the same. So over here, amount of work done, 1,000 compared to 10. So they're trying to see if they can trick you. One, they might think you're going to pick less, and the other one you might pick more. And it doesn't depend on the distance either, because it's an equipotential line. The radius is the same. The V is the same. Same answer. Both will be 0. You will get that. Okay. Moving on to I think this is the last page of the multiple choice questions. Let's see if I can finish this off. What's the electric potential this far away? So the potential is simply V equals KQ over R. Not squared, just R. I will go through those in another video, knowing when to square it and when not to. But using this rule, we have everything. 12.5 pico. Pico is times 10 to the minus 12. It helps to remember that. 45.5 centimeters times 10 to the minus 2. I'll just divide by 100. Put the numbers here. 9 times 10 to the 9 multiplied by 12.5 times 10 to the minus 12 divided by, not 45, 12.5, divided by 45 times 10 to the minus 2. Putting that in your calculator, I'm not going to write it out, it'll take me forever. If you do that, you will get 0.247. Over here, similar to a previous question without the numbers, this time we have numbers. You are at this corner of the triangle because these two have charges. The third corner, which is this one here, it says right corner. Well, it doesn't really make sense because we have these two things, so it's technically the bottom left. So you will do V1 plus V2. V total is going to be, that's a T, V1 plus V2. That's a plus. My handwriting is atrocious today. All right. You will do KQ1 over R plus KQ2 over R. You will include the minus in this case. So you will write negative 2 micro times 10 to the minus 6 centi times 10 to the minus 2. If you solve them both together, adding them, you will get this number here, 4.5 times 10 to the 5. Try it yourself, okay? You'll do KQ1 over R plus KQ2, including the minus, over R. So technically you're just doing a subtraction. And that's you done. Okay. A distance here, what will be the difference when you change the distance to divided by 4? So this we can use the trick. So V equals KQ over R. Normally I can set everything to 1. If I was to set it to 1, everything will just give me 1. What I'm now going to do is I'm going to change it. I'm going to change the distance to divided by 4, which is a quarter. So what I'm going to do is I'll keep everything else the same, just like we did previously. 1 times 1. I know this is supposed to be 9 times 10 to the 9, but I'm going to consider it as 1 because I'm not changing it. 1 times 1 divided by not 1 anymore, 1 over 4, a quarter. So by doing that, you'll realize, sticking it in your calculator if you want, this will come up, you'll end up getting 4. 4V would be the answer. So that means we will get this. What happened here? What have I done? I've already solved this one as well. I'm pretty sure I erased my writing earlier. Anyway, so if you're trying to figure out what am I trying to figure out? The potential, the V. You're trying to figure out the V. So if I was to draw a square, and I had two places. I had where am I doing it? Each has a charge of plus E, the length of the side, so in the opposite corners of a square. So one corner here, the opposite corner would be here. That's fine. So you will both have a positive E, so that will be an E, that will be an E. That is my charge. The length is the L's, and we are trying to see the empty corners, so we can do it here. Both will be the same idea. The calculation will be the same, so I picked this corner. So I will just do V equals KQ1 over R plus KQ2 over R. Okay, so what I'm going to do now is I'm going to replace the values with what I have. So what I'm going to do is K stays as K, Q just becomes E over R, which is the length, and so it's just L, KE over L, plus KE over L. So if you know how to add, like for example, A plus A, for example, there's a little bit of math revision here. A plus A equals 2A. Just keep that in mind, yeah? Because if I said to you A times A, that would have been A squared. So this is just something to remember about basic algebra, okay? So we can consider these and these as, well, A or whatever, any letter, they're the same. So adding these together, this plus this is two of them. So I will write 2 KE over L. There's two of these, so, or I can just multiply by 2. Same idea, yeah? So you get 2 KE over L. Basically using this rule over here. I have 2 of these. So that means 2 KE over L, D would be my answer. That's the way to get this one. All right, almost done with this. This is my longest video yet. Continuing on with this one, we're trying to find the potential energy of a system of 3 equal charges. Potential energies U equals KQ1 Q2 over R, not squared either. So you're going to do this one, and there are 3 equal charges. You have the energy here. You want to find the charge of one of the 3 charges. So if you're going to try to find charge of one of the 3 charges, you solve for Q. Well, there are 3 of these. So what I can do then is I'm going to have 3 of them. So I could do something like this. And you're going to find the charge. So you will have to do 0.54 equals, and there's 3. So basically you add, you do it 3 times. K, which is going to be multiplied by 9 times 10 to the minus 9, multiplied by Q times Q will just becomes Q squared. And I'm going to divide that by the distance, which is 0.33, 33 centimeters. Solve for Q. Well, actually, if you solve it for Q squared, you will take the square root at the end to get Q. And if you were to do that, you should get 2.6 microcoulombs. 2.6 times 10 to the minus 6. Over here, we're trying to see what will happen when the 2 charges separate to a distance. The potential is U. What will happen if the distance becomes D over 2? Same idea. So, U equals K Q1 Q2 over R. So if I set everything to 1, just like I did here, but change only the distance, I will call it 1 times 1 times 1. That just gives me 1. Divided by D over 2, a half. If I put that in my calculator, I will get 2. 2U. So the answer would be C, 2U. Each of the following pairs of charges has this distance. Which one has the highest potential energy? So you can actually just check the difference between these two, Q1 and Q2. These two are both positive, so you'll add. These two are negative, so you'll subtract. These two also opposite, you will subtract. So you can clearly see this will be 8, a difference of 8. This is not, there's a difference of 2, and that is also a minus 2, but yes, a difference of 2. So the energy, the highest, will be between these two, which kind of makes sense because they don't like each other. They are both going to repel. These two will kind of attract. They'll be happy. These two will also kind of attract. They will be happy. So that's an easy way to remember this. And I am done with this topic. Thank you.